So yeah, hello everyone. Thank you for joining us at QSide Day 2. We had a wonderful program yesterday. There were many speakers, and we continue to have about 12 talks today. So we look forward to showing all the work that we have compiled to you throughout the day. So today's keynote will be given by Professor Bouchard. I'm sorry. Frédéric Bouchard is a research officer at the National Research Council Canada. He completed his PhD in quantum optics at the University of Ottawa with a focus on quantum cryptography and high-dimensional quantum information. He joined the Security and Disruptive Technologies Research Center of the National Research Council in 2019 as a research associate working on photonic quantum information processing and became a research officer in 2022. So without further ado, I would invite Professor Bouchard to take the floor.
All right. Thank you very much. So you can hear me fine? Everything's good?
Yep, we can hear you in the room.
Perfect. Awesome. Yeah, so I would first like to thank the organizers for putting together this wonderful conference and inviting me for this keynote presentation. And you'll see, so the way I structure the talk, I try to have the majority of it very fundamental stuff, not showing too many results from research, but still putting a bit towards the end, but really kind of covering what are the fundamental concepts of quantum cryptography and more generally how it fits in this more general quantum technology environment. So as mentioned, so I'm at the National Research Council in Ottawa. And so I'm in this building here, which is a really cool building, super old. There's a bunch of history. If you ever get to visit it, it's really cool. There's some hidden labs in the basement that you're not supposed to go see, but there's some very cool stuff there. And I'm part of the quantum technology group where we look at a bunch of different things from quantum memories, quantum frequency conversion, quantum computing, and quantum cryptography. But we're mostly looking at applications in quantum technologies with photons, essentially. So here's a picture of the group that's not up to date, actually, but yeah. And so it's in Ottawa. So Ottawa is great if you're an outdoor enthusiast. During the winter, you can go skate on the canal. There's a bunch of bike lane, and it's a great city to be in. There's the University of Ottawa just next to the National Research Council, so it's a very unique environment to do research. And let me start right away with the acknowledgement slide, which people usually put at the end, but I like to flash it right in front. So those are the people with whom I work at the National Research Council and some of the collaborators at the University of Ottawa and other international collaborators. All right, so I'm gonna start with a slide you've probably seen a few times so far in this conference, and you'll probably see more, which is introducing the field of quantum technologies and how we basically start from this and focus to quantum cryptography. So please bear with me. And of course, what we mean by quantum technologies is not just technology based on quantum mechanics, such as lasers or transistors, but really looking at this kind of quantum weirdness. So these new concepts that are maybe hard to grasp from a classical standpoint. So this is quantum entanglement, the uncertainty principle, the superposition principle. And the question is, can we get any new types of technologies with these spooky concepts? And generally, we divide quantum technologies in three fields. So the first one is probably the most obvious one and the most well-known. So quantum computing. Applications of this would be, well, just a full universal quantum computer. There are some intermediate application like a quantum simulator. Another field is quantum communication. So this is where you want to distribute information at the quantum level. So one example is quantum key distribution or quantum cryptography, but there's also other applications of quantum communication, not in cryptography. And finally, quantum sensing. So this is essentially how can you measure things more accurately. So one good example is the detectors of gravitational waves. right now they're really pushing the limit to what can be done, and they're hitting a wall in terms of what can be done classically. So they're actually looking into some quantum states, so squeeze states, for instance, to measure these gravitational waves more accurately. All right, so if you want to do quantum technologies, so those are the different applications, but you first have to pick your quantum system. So this is where the information will be encoded. So it can be spin systems with quantum dots, trapped ions is another one, superconducting qubits, cold atoms, and photons. So those are a few examples. Of course, there are more of them, and they all have their own advantages for different applications. But the one we're interested in is photons. And what I mean by photon here is really we're encoding the information on the photon, because of course you're probably going to have a laser in all these other systems to control it or detect the quantum state. But here we're really talking about encoding the information on the photons. So then this is what our group is interested in, this photonic quantum technologies. And actually you can use photons in all these applications. So quantum computing, there are actually some companies looking at how you can perform quantum computation using photons directly. And of course, quantum communication, that's the most obvious one, because you probably wouldn't use another quantum system to distribute information over long distances. And the same thing with quantum sensing. All right, but the topic of this talk is quantum cryptography. So this is just to give you an overview, and then I'm going to focus on the subject of quantum key distribution. So there won't be too much math. Actually, I think there's maybe 1 or 2 slides with math. I really want to give you sort of the intuition or the bigger picture of what is quantum cryptography, and what is the motivation for it. So to do this, we have to start with cryptography, so just classical cryptography. And the way this is usually introduced, you have 2 parties, Alice and Bob, instead of saying person A and person B, and they are connected through a communication channel. And this is completely classical. So this could be a landline. You're just calling. So Alice is calling Bob, and what they want to do is communicate. So they want to send a message from Alice to Bob. And this is not an issue. There are different ways to do this. But if the message is sensitive, you have to look at how you can actually encrypt the information, because an eavesdropper could be listening at the communication channel and be listening at your conversation. In some cases, that's not necessarily what you want. So what you use is use a key. So in cryptography, Alice and Bob would meet at some point. They would share a key. So they need to be identical, and they need to be secret. So only they know what the key is. And then what they do is they can start with a message, encrypt the key, and then send the message through the communication channel. And if the eavesdropper is trying to listen, so the eavesdropper we usually call Eve, she's basically gonna hear random noise. And here I'm using this picture of actually taking the key and encrypting the message. But what you're really doing is you're generating a bunch of zeros and ones that are random, and then you're adding this to your message. But I kind of like this picture of thinking of an actual key. The problem with this is, so it's not, okay, yeah. Once you've used your key, you cannot use it again. Because if you use your key again and again, the eavesdropper could start figuring out, okay, maybe the key looks like this, so then she could get some information about your message. So this is why this type of cryptography scheme is called a one-time pad. So you use your key once, then you throw it out. Now the problem is, if Alice and Bob want to exchange secret information again, they have to meet up again and generate this secret key. So this is not super practical, especially if you want to send emails every day and you don't want to fly to Europe. I don't know if you're communicating with someone in Europe. So there's this thing called public key cryptography, which allows you to share a key over a certain distance. So the way it works, you start with a secret key. So Alice generates a random key that's only known to her. Bob does the same thing. And from this, sorry, they can obtain a public key. So there's a way to do this. And the important thing is it has to be easy to go from the secret key to the public key, but it has to be hard to go from the public key to the secret key. So there's an algorithm to actually calculate how to obtain the public key from the secret key. And the whole point of cryptography is you have to make this hard. You have to make going from the public key to the secret key hard. And then they exchange the public key through the communication channel, which means the eavesdropper has access to the public keys, but she doesn't have access to the secret keys. And then what you do is you encrypt your message using both the public key and the secret key. And since the eavesdropper only has access to the public keys, then she's going to see random noise. So that's basically the whole point of public key cryptography. There's some details I'm leaving out, but that's the big pictures. The big picture you should have in your mind. Now the problem is, I didn't say it's impossible to go from the public key to the secret key. It's just really hard. And if the eavesdropper had access to some sort of supercomputer, well, it could be possible to go to actually obtain the secret key, and that would be an issue because then the eavesdropper would have all the secret and public keys, and she could actually listen at the conversation. So this is basically what we're afraid of in cryptography. And now the question is, what is the supercomputer? So what is it doing? Actually, it's something very simple. It's decomposing a number in terms of its prime factors. So for 15, that's pretty easy. But if the number is really, really large, this can be quite hard with a computer. So you need a supercomputer. And fortunately, we can actually make these keys hard enough to go from the public to the secret with current computers. But what we're afraid of is quantum computers, because there is an algorithm that basically tells you how to do this with a quantum computer. So as soon as the eavesdropper has access to a quantum computer, we're kind of screwed. So this public key cryptography is what we're using to encrypt emails, to do bank transaction, and like our whole cryptography infrastructure is basically based on this. And at the moment, some very smart person at this conference comes up with a quantum computer and makes a company and sell it to an eavesdropper, then we're screwed. And another point is the eavesdropper could be saving all of our emails that are encrypted. So at this point, it's just noise. It's random messages. And she could just wait. And let's say in 10, 20 years, when there's a quantum computer available, she could decrypt all these messages and kind of get sensitive information that maybe you wouldn't want an eavesdropper to have access to. So we have to think about solution to the event of quantum computers coming in the future. And as I'm sure you will see in this conference, this is coming very soon. So there are a few different options. So the first one is called post-quantum cryptography. So the advantage of this is you keep the same hardware, but you change your software. So the idea essentially is you make it harder to go from the public key to the secret key. And in particular, you think about quantum computers and what algorithms you can run on the quantum computer, and you basically try to make it hard for quantum computers as well. But you're not making it impossible to go from the public key to the secret key. You're just making it harder. So you're saving yourself some time in that respect. And another way to think of it is, you could have, in our whole cryptographic infrastructure, you might have some data that doesn't have to be too secure. So you could just basically use the normal public cryptography. If you have something that's more sensitive, you could use post-quantum cryptography. But if you have information that you really, really don't want anyone to have access to, even in the future, then this is not 100% safe, because there could be more algorithms or better quantum computers in the future that could also break this post-quantum cryptographic schemes that we're looking at. So another solution is quantum cryptography. And the trick here is not only we're changing the software, but we're also changing the hardware. So we have to add a new type of channel on top of the classical channel. And this is called a quantum channel. So this can be through a fiber. It can be a free space channel. So literally like a free space line of sight in an intra-city link, for instance, or it can be with a satellite. But the important thing here is you should be able to send single photons where that are carrying quantum information, and they should be able to make it through the quantum channel. So this is difficult potentially. And the way it works, so this is called quantum key distribution because you want to generate a key and you want to distribute it through a quantum channel. So Alice will generate a key. She will encrypt it on a single photon's quantum state. She's going to send the single photon through the quantum channel. Bob will measure the single photons. He's going to get the key. And then boom, they both have a shared secret key. They can encrypt a message, send that message through the classical channel, and boom, the eavesdropper, since she doesn't have the key, she can't read the message. And of course, so this is the case, the first case where, okay, once you've used your key, you have to throw it away. So this is a one-time pad, which is fine. You just need to send another photon with the information encoded on it. And then whenever you want to send a new message, you have to send a new photon through the quantum channel, roughly. Now the problem is, okay, the eavesdropper is always listening at the classical channel, but what happens if the eavesdropper also listens at the quantum channel? So if Alice is preparing a state, sending it through, and the eavesdropper is trying to get just a little bit of information out of the photon state, we know from quantum mechanics that whenever you're trying to get information from a quantum state, you actually need to measure it. And when you measure it, you're going to disturb it. So when Bob will measure the photon state, he's going to get a slightly different information than what Alice sent. And then one of the things they can do is they can call each other on the classical channel and compare their key. And if they see that, okay, the key is slightly different, they have to assume that this is coming from an eavesdropper listening at the channel, and they have to throw away the key, which is bad, but it's not as bad as the eavesdropper having the key and listening to the conversation. So now they're just sharing a key. They're not sharing sensitive messages. Okay, so this is essentially the idea of quantum cryptography, the first order. Now let's go in a little more detail. So I'm gonna just go one level deeper and try to tell you a bit about how the protocol itself works. So this was invented by Charles Bennett and Gilles Brassard in 1984. So this is why they call it the BB84 protocol. And this is how you go from the key, the classical key, which is just a bunch of zeros and ones, to the quantum state. So this is based on mutually unbiased bases. And the idea is you can encode your qubit in different bases. So I'm sure you learned yesterday that a qubit can be in the computational basis. So that's either a 0 or a 1, but a different basis is the superposition basis. So it's this plus and minus, where the information now is in the relative phase of your superposition of 0 and 1, so either plus or minus phase. And one of the interesting thing about these two bases is if one prepares a state in the first one, but someone else measures in the second basis, then you don't get information about the first basis. So basically, if you want to be able to get a correlation, you actually need to measure in the same basis. So what Alice does, she's going to randomly send different states from these two bases. So here I'm using the example of polarization. So your 0 and 1 will be horizontal and vertical polarization, and your plus and minus state are going to be diagonal and anti-diagonal. So Alice is going to send a bunch of random polarization states, and she's going to assign a 0 or a 1 to each of them. So if you're in the first column, it's going to be a 0. If you're in the second column, it's going to be a 1. Now, Bob will basically decide which basis to measure in, and this is going to be chosen randomly. and then he's going to measure the photon state. All right, so let's say this is what he's measuring. And then he's going to do the same thing. He's going to assign a 0 or a 1 depending on what he measured. So this is what you get. So as I mentioned before, you don't get information if the photons were encoded and decoded in different bases. So what they're going to do, they're going to call each other on the classical channel, and they're going to compare notes. They're going to say, okay, this first photon was encoded in the first basis. What about you? Yep, first basis. Let's keep this. Great. The second one, nope, we didn't pick the same basis. Let's throw that away. And when they're doing this, they're not giving up information about the key. They're only giving up information about the basis, which is fine. And then they're going to throw away all the bits where the bases didn't match. And there you go. Now they have two keys that should be identical and should be secret. But one thing you notice here is, oh, in one case, Bob measured a 0, but Alice actually sent a 1. So what's going on here? Well, in real life, you're always going to get errors. So either they're coming from noise in the channel or imperfect generation and detection devices, or even from your detectors. So you're always going to get noise. But the question is this noise or error bit coming from an eavesdropper, or it's actually just noise? So there's actually a way to characterize this. So first you have to determine what is your quantum bit error rate, Q. And this is just the number of errors you have divided by the length of your key. So here you have 1 error divided by 5. And so here's the slide with math. I promise there won't be more math after this. But the quantity you're interested in is the secret key rate, which tells you how many bits of information you can get per photons. And generally, this is given by the difference in mutual information between Bob and Eve. So Alice and Bob will have some mutual information they share between their keys. But the eavesdropper can also be in the quantum channel, kind of trying to get information. So the eavesdropper will also have some mutual information with Alice. And what you want is you basically want Alice and Bob to have more information than Alice and Eve. And as soon as this is the case, you should have a positive secret key rate. Another way to calculate this is to say, okay, you start with your full key, but then you're going to have to throw away some keys to do two things. So the first thing is error correction. So Alice and Bob, they have keys with some errors. So they have to get rid of these errors. So there's a protocol to do this. It's called error correction, but it's going to come at a cost. So you're going to have to give away some keys. So this is fine, but the eavesdropper could also be doing this. So the eavesdropper will also have a key with less errors. But now you have to do the second step called privacy amplification, where you give even more keys up, but then you're making sure that the eavesdropper doesn't have any information about the shared key between Alice and Bob. And of course, this can only be done if Alice and Bob have more information than Alice and Eve. And there's actually a way to calculate how many keys you have to give up. And this is given by Shannon entropy, which is a way to measure the information from your key. Okay, so let's just move this to the left. So this is our formula, and it can be useful to plot this. So the dashed line here is just 1 minus the error correction. So you have two keys. So you have information with some errors, and you want to get rid of them. And this is classical communication, basically. If you're transmitting some information, there's some errors, there's a way to get rid of these errors. And what you see is the curve never really quite get to 0. It only reaches 0 when you have 50% errors, which basically mean you have completely random data. So this is classical communication. You can send information from North America to Europe to Asia, and if you have errors, you can get rid of them. That will cost you some bits of information, but you can always just send more. Now, the issue with quantum communication is there's that second step, privacy amplification, and this is costly. What you see is now the curve, the solid curves crosses the 0 axis at around 11%. So you basically have an error threshold, and what that means is if Alice and Bob are communicating through a quantum channel, and there are more than 11% errors, there's nothing you can do. You cannot just send more bits and hope to be able to exchange quantum information. It's basically done after 11%. And this is why quantum communication is so much harder than classical communication, because you really need to keep your errors low. So this limits the kind of distances that we can consider. All right, so in a nutshell, this is how you can characterize your quantum communication. So now, if we look at the full quantum key distribution system, so there are different components, which I sort of mentioned. So the first part is the sender. So that's Alice. You need to be able to generate single photons. So there are different types of sources. There are heralded source, attenuated lasers, quantum dots. They all differ in terms of complexity and efficiency and fidelity and all these things. And it really depends on what's your budget and what kind of system you're trying to establish. You should also be able to encode the information on your single photon. So that's your zeros and your one. And you want to be able to do this quickly with high fidelity. On the receiver side, you actually need to detect your single photon. So there are different single photon detectors with different complexity, different efficiencies, and you should be able to extract the information from the photons. In between, you have the quantum channels. So I mentioned a few. So you could have an intra-city link or a quantum satellite. And I encourage you, I think Tanya has a talk later today, and she's going to talk about KeySat. So this is this Canadian satellite project where you want to send photons to the satellite to establish quantum communication links. There's some fiber channel is an obvious one. There are two types of fiber networks you can think of. A bright one, which is essentially the ones we already have, but you would keep a band of frequencies where you could send your single photons. Obviously, there's some issues there because you might be getting a lot of noise from your bright classical communication channels. Or the other option is to build a completely separate fiber network only for quantum communication. We usually call that a dark fiber network. But of course, now you're completely changing your hardware, which can be costly. And there are other types of channels. So you can look at quantum repeaters in your channels. We even looked into underwater links if you want to communicate with submarines. Then you have the quantum protocol. So I mentioned BB84, but there are actually a lot of different protocols which have different advantages and different for different conditions. And the classical protocol, and that's error correction and privacy amplification. And once you have all of these ingredients together, then you have a full quantum communication system. Okay. So I've been talking about encoding information on photon. I mentioned polarization, but actually photons, or just light in general, it has many different degrees of freedom. And the question is, which one is most appropriate for the specific task you have in mind? So let's list all these degrees of freedom. So polarization. So this is basically the electromagnetic field is oscillating in a certain direction, and you can use this at the single photon level to encode the information. So horizontal, vertical, diagonal, anti-diagonal. You can encode the information in the arrival time of the photons. So this is called time bin encoding. And you're really just preparing a single photon in a superposition of these different time bins. One advantage of time bins versus polarization is polarization is inherently bidimensional. So it's a qubit. So you can only have a 0 or 1. But time bins can go 0, 1, 2, 3, 4, as much as you want. But it's still a single photon, but you just have more modes to encode the information. You can do the same thing in frequencies. A different wavelength would correspond to different states. There's actually a very interesting way to combine time and frequency to form these things called temporal modes, where the information is not just in time or just in frequency, but it's both together. And you have these overlapping modes in intensity, but they're still orthogonal. So you can use them to encode quantum information. The other degree of freedom that light has is the spatial transverse degree of freedom. So position, if you have a waveguide, the information is encoded in the position of the photons. You can also encode the information of momentum And similar to how time and frequency, you can form temporal modes, you can use position and momentum to form spatial modes. And one very popular way to encode the information in spatial modes is these twisted beams of light. And depending on the twisting, you get different quantum states. So this is a bit of an overview. Now I'm going to talk a bit about time bins. So this is one of the things we're interested in our lab, how to encode information in time bin and how can this be used in quantum communication. So as I mentioned, if we start with qubits, the information is encoded in the time of arrival of your time bin. And one important parameter is this delta t, is how far apart these two pulses are in. So that would be your first basis. The second basis is the superposition. So that's the plus minus basis. And there the information is encoded in the relative phase of the two pulses. So if you look carefully, you can see that the carrier are actually off by a pi phase. And then you have all the ingredients that you want to encode the information for a BB84 protocol. You would randomly pick one of these four. And the question is how you actually measure them. So in the first case, it's pretty easy. You just send your time bin state on a detector and you measure what time they arrive. But then how do you measure the relative phase between two time bins at different times? And this usually involves an interferometer. So what you do is you split your state into two paths and you delay one and you re-interfere them. And depending on the relative phase, you're going to see the photons exiting different output ports of an interferometer. So what you look at is this central pulse, and this will tell you about the relative phase. Okay, but one of the problem with this is now you have this big, bulky interferometer, and you actually need to match the path difference of one of the arm to the delta t, basically. So if delta t is large, so let's say you have a 1 nanosecond time difference, this is what you would want for using something like an avalanche photodiode detector. But to measure in the second basis, in the superposition basis, you actually need a very large interferometer. So this is not so practical if you want to send this on a satellite or if you want to have phase stability. So one solution that we're looking into is, okay, can you decrease delta t? Can you encode information at a smaller time scale? So moving to hundreds of picosecond, now you have to use a different type of detector, which is fine. There are these superconducting nanowire detectors that have this kind of temporal resolution, and you can then make your interferometer more compact to measure the relative phase between your time bins. But the question is, let's say you want to go all the way down to picosecond, which can be done, like it is pretty straightforward to generate pulses at the picosecond level with ultrafast lasers, but we don't really have good detectors that can measure photons with temporal resolution of 1 picosecond. So how do we do this? Well, first, if you want to measure the relative phase now, the difference in path of your interferometer is going to be very, very small. It's going to be a fraction of a millimeter. And this is very useful because now you can have this big, bulky interferometer on the right and be replaced by a very thin crystal that can achieve the same thing. So this is good. But how do we measure in the computational basis, so the time of arrival? And what we do in our lab is we actually use nonlinear optics to measure these photons. So what you do essentially is you use a strong pump pulse that has a pulse duration of picosecond, and you can use this to interact with a single photon to measure its time of arrival. And one way to think of this is there's a point where you need to use optical techniques to measure your photons if you're short enough. But if you're long enough, you can use a lot of these electronic techniques. So one scheme that we use a lot in our lab is using the nonlinearity of a fiber, essentially. So think of sending a single photon through a fiber, you're going to get it out. But now if you overlap your single photon with a strong pump pulse, it's actually possible to rotate the polarization of that photon to 90 degrees. So they're actually interacting with your single photon at the picosecond level. This can be very efficient, and you're not introducing too much noise. So we basically have the equivalent of a picosecond temporal resolution detector for your single photons. Okay, so how would this look like in a quantum cryptography in a quantum cryptography experiment? Well, you would prepare your time bins in a superposition. You overlap your strong pulse with one of them, you rotate, and then you're basically turning the time bin information to polarization. And this can be measured with the polarizing beam splitter. The superposition, you just have to throw in your very thin interferometer, so which is this birefringent crystal, and you can measure the superposition. So you have all the ingredients to do a quantum cryptography experiment with time bins instead of polarization. And one of the advantages, so here we're measuring the 4 BB84 states. And what we see is we get really good quantum bit error rates. So this is the fidelity above 99%. And this is very stable over time. So we think this could be very interesting for these kind of second generation quantum communication systems. Another application I'm just going to mention here is you can actually use this as a temporal filter. So let's say you have a long pulse going in and you have a short pump. You can actually filter temporally the single photons coming in. So why is this useful? Well, if you're encoding your single photon in a single temporal mode, so you have these Fourier transform limited pulses, this is how you can basically be most efficient in terms of how dense your quantum information is. And this is important when you think of noise. So let's say you're trying to do a quantum communication experiment in a free space link. Well, usually this is only going to work at night, because as soon as the sun comes up, you're going to get a lot of noise photons, and this is going to increase your quantum bit error rates above 11%, which is problematic. So you have to think of how you can filter out noise and what are the best techniques to do so. So you could have your single photon here, your quantum signal, which is flooded by noise. But if you have a good temporal filter, you can get rid of all the noise in time, but then you're still stuck with all the spectral noise, but then you can apply a spectral filter. And then when you have these two together, your quantum signal can still be pretty good compared to the amount of noise you have. And one way to think of this is, even if your single photon is flooded by noise coming from your channel, if they're arriving at different times and have different colors, you can actually filter that out. And this would give you roughly a factor of 1,000 better improvement in terms of noise resistance compared to our current systems that we have. And the whole point of this is, it would be nice to be able to do these experiments just not just at night, but also during the day when the sun is up. So this is the example if you're thinking about a satellite. So you're paying a lot of money to actually do these experiments with the satellite, but you can only use it half of the time. So we want to use it in daylight condition. But then the other example, as I mentioned before, with the fiber network, if you're not making a completely new dark fiber network just for quantum communication, and you want to use the ones we have right now, well, all this bright classical communication is going to generate a lot of noise. So you need to make sure you know how to filter that out, and our technique would also work for this. Finally, I'm just going to mention one other project that we're interested in our lab. And this is how you can encode more information on your single photon. So not just a bit, a 0 or 1, but 0, 1, 2, 3. And there's some reason why you'd want to do this. So one example is, if you have a communication link where you're limited by the saturation of your detector. So your detector is detecting as many photons as it can, but you want to increase your rate. One trick is to encode more information per detected photons. So in this way, you can improve your rate by a factor of 2, 3, 4. But this is more tricky, because now you still have two bases to encode the information. So there's the computational basis, which is the time of arrival. But then you might ask yourself, okay, how does the superposition basis looks like now? Because it's not just in phase or out of phase. It's a little more complicated than that. And the information is still encoded in the phase, but it's basically this, as you can see, this 0, 0, 0, we would be one state, and that's orthogonal to 0, 0, pi, pi. And you have also these other two states. And now the question is, how do you actually measure this overall relative phase for all these pulses? So it's a little more complicated than just one interferometer that can measure the relative phase. But with our platform, with our ultrafast pulses, we can actually build a setup that can measure these different states. And this could be used in quantum, in a quantum communication scheme where we're essentially increasing the amount of information per photon. And this is an experiment that we did recently, and we actually get pretty good results in terms of how well you can extract the information out of the photons. All right, now I'm going to show a bunch of pictures. So we want to test these things not just in the lab, but in real life environment. And one of the thing we did is we established a free space link over the city of Ottawa. So this is the campus of the University of Ottawa. And what we did essentially is we brought up our single photon sources on the roof of 2 of the buildings there. So the first experiment we did was a free space channel of 300 meters. So you can see this is a picture from Google Map. And we encoded the information there in polarization and spatial mode. And you have 2 pictures here from the point of view of Alice and Bob. So I was on the Alice side and my colleague were on Bob's side. And one of the questions we had was which way, like who is going to be Alice and who's going to be Bob? And if you look at the picture of Bob's view, just next to the white circle, what you see is the Parliament of Canada. And on the right, and on the left, you have the National Defense. So we thought maybe it's not the best idea to shoot a laser that if we missed on one side, we're shooting a laser in the building of the National Defense, and on the other side, we're shooting on the Parliament of Canada. So we decided that this building would be Alice, and that would be shooting the laser on the other side, where, as you can see, the Alice view picture, there isn't too much going on. But what we did is essentially we went there at night, generated single photon, encoded the information, send them through, and then detected them with single photons. And we're actually able to establish a secure link there. When you go in these real life conditions, you get a lot of new issues that you don't necessarily get in the lab. And one of them is turbulence. So you have atmospheric turbulence. And since we did this during the winter, there are a bunch of buildings in the free space link, and the heating of these buildings actually gave a lot of turbulence in our link, even though it was pretty short. So the next step is we wanted to extend this to a longer distance. So we went from 300 meter to 5.4 kilometer. And now this is between the University of Ottawa and NRC. So NRC has a building that's 5 kilometers away from the University of Ottawa. And instead of just having our single photon source just on some breadboards, we decided to do a proper job and build a shed with a deck and have an optical table in there, so we could actually do more complicated thing. And one of the things we're looking at right now is we have an adaptive optics system. And the idea there is you actually want to compensate for the atmospheric turbulence. And the reason why this is hard is because this is happening on the millisecond scale. So you need a very fast way to measure the turbulence and compensate for it. So that's one of the thing we're looking into. We also looked at different types of quantum channels. So an underwater channel, some people were interested in doing this, but we're only doing it in the lab. So we decided to go outside and actually do this in a swimming pool. And then we extended the communication distance to, we have these flumes facilities at the NRC where we could fill it up with water. And then you see here on the right, the single photon source, and we send our photons through the water link. And finally, the goal would be to have all these different types of channels. So you have short intracity free space link with fiber links. And if you want to connect them, you have to do this with a quantum satellite. And yeah, this is how you would have a quantum network over Canada, basically. So this is it. So in conclusion, those are all the different parts of a quantum communication system that if you want to build this, you have to look at all the different components. And a lot of the things we learn in quantum communication can actually be applied in different applications of photonic quantum technology. So this is why we're using a lot of these techniques in quantum computing, quantum sensing as well. So yeah, so to finish, so this is the quantum technology group at NRC. So there was a photographer taking a bunch of fancy pictures. So here they are. And I also wanted to mention that we're always looking for really good students and postdocs. So if you're interested, please contact me and you can have a look at our website if you want to know more about what we're doing. And that's it. Thank you.
Did you get the co-host?
Yeah.
Can you still hear me, Professor?
I do, yes.
Okay. Yeah, thank you for the beautiful talk. It's a nice way to get started with our second day cryptography. It's going to be a big thing. I'm sorry. There's an echo in the room.
Yeah, I can hear it too, but it's I can
Hello,
hear you.
is the echo now?
That's better, yeah.
Yeah. Echo. Hello. Yep. Okay. So yeah, the echo's gone now. Sorry. So we do have time for Q&A. We could start with our in-person.
Thank you for the presentation. On one of the slides where you were discussing the different degrees of freedom for photons, for the spatial modes part, is this slide polarized circularly, or is it a completely different thing? In the bottom right corner, you had a figure where you showed some visuals of what those photons would look like.
Yeah, I can go back to it. It might take a while, but yeah. So it's not circular polarization. So it's a completely different degree of freedom. It's gonna take a while, but yeah, I can explain. So the polarization is only about the direction of oscillation of your electric field. What I mean by these twisted beams is literally the wavefront. Here it is. Okay. Did I go too far? No. Okay. It's going to come back at some point. But the wavefront is twisted. So if you have a plane wave, you essentially have a beam that's propagating, and you have these plane waves of these planes of constant phase. With these twisted beams, you actually have a phase that it's not a plane anymore, but you have constant phases that are twisting. And people have been using these twisted beams to, you can actually interact them with matter to rotate small particles. They're orthogonal, so you can use them in communication. They're orthogonal, and we use them a lot in quantum information. So not just quantum communication, but also quantum sensing. If you know about STED microscopy, this is what they actually use to achieve high resolution. Yeah, but it's completely different than circular polarization. It's really, if you look at the beam itself, so if you shine the beam on a piece of paper, it's going to be a donut. And if you had access to the phase, you'd see the phase would ramp from 0 to 2 pi. Yeah. Sorry, it was all over the place with the slides.
Any more questions?
Sorry if it's a bit off topic, but I wanted to ask, is it possible to use a quantum entanglement to distribute quantum keys, like distribute a pair of entangled particles, and then Alice, for example, can change, make a change to her version of the particle, and Bob has the same change reflected, so the key information is effectively distributed?
Yeah, so absolutely. So that's a good point. Everything I've mentioned so far is called prepared and measure. So you generate a single photon, you encode the information, and then you just send it to Bob. Another way to do this is called an entanglement-based source, where you just generate pairs of photons that are entangled, for instance, in polarization, and then Alice keeps one photon, sends the other one to Bob. And the advantage of this is you basically get this randomness between the different bases and the different states from the entanglement. So all Alice has to do is measure in a certain basis, and Bob measures in a different basis, and it's completely equivalent. So, and when you do these security proofs of the theory, it's actually easier to do it with an entanglement source formalism. So this is how people do security proofs, actually. But it's completely equivalent, and there's some reason to use an entanglement source sometimes, or a prepare and measure source, depending on what kind of experiment you want to do. Yeah, thanks. I can't hear you. I don't know if you're.
So I can. Okay. So what are the QKD protocols that you have implemented so far? That's one of the questions from chat.
Sorry, can you repeat this? There's a bit of echo right now. I had a hard time getting that.
Can you hear us now?
Yeah, okay, that's better.
Okay. So the question from the chat is, what are the QKD protocols that you have implemented so far?
I guess I can just read it from this. Choose a certain photonic. So it's this, is there a reason for the choice of certain photonic degrees of freedom over others in practical application? Oh no, what are the QKD protocols that you have implemented? So, okay, so the BB84 protocol is essentially, it's probably the simplest one, but also the most useful one. A lot of these demonstrations are still using the BB84 protocol. At the end of my presentation, I talked about encoding more information per photon. So there you have to use a different protocol. So this is usually called a high dimensional BB84 protocol. Another class of QKD protocol are called tomographic, where the measurements that you're making are actually sufficient to fully reconstruct the quantum state. So you actually need to measure in more bases. So not just a MUB 1 and 2, but also 1, 2, 3. This is less efficient, but lets you tolerate more noise. So your error threshold can move around. I mentioned there, like this twin field QKD, which is more loss tolerant, but we essentially looked at different protocols. Yeah. Then I see there's another question in the chat. I can maybe answer this one. So is there a reason for the choice of certain photonic degrees of freedom over others in practical application? Absolutely. So polarization is very easy in terms of generation and detection, because you can just use wave plates and polarizing beam splitters. But in fiber, they can be a little tricky. So there are things like polarization, mode dispersion, birefringence. If you're communicating with the satellite, there could be some issues with the mirrors, but it's usually a very robust one. Time bins are very good in terms of transmission through the quantum channel, but the detection is more tricky. So depending on what system you're looking into, there's some advantages for all the different degrees of freedom. You really just you have to look at one application. Yeah.
Yeah. Thank you, Professor, for the wonderful talk. I think that's all the time we have for question and answers. So let's thank Professor Bouchard one more time for the keynote.
Thank you.